I'm going to share my screen. Should have my screen now. Put this down here. So today's class, we're going to prepare for your next component of the assignment. I think it's assignment 2, and we're talking about column load development. Okay, so this applies to multi-story buildings, and so looks very much like your project you have. And what we need to do is find out what loads are coming down in each of these columns. If you remember from strength of materials, we design columns for axial loads, so loads that are along the length of the column. And very important to figure these out. We also know that we have different loads: snow load, live load, and dead load. Live load's due to occupancy, snow load's from the roof and snow, and then dead load is the weight of the structure. And when we look at the weight of the structure, we're looking at weights of columns, weights of the floor, weights of the walls, and now comes into play the geometry of the section. So before we go further with this, you have your handout in front of you. Just going to switch screens here, switch to SketchUp. And you see here, and just kind of show you the building construction process. For 4-story buildings modeled in SketchUp, and we design buildings from the top down, we build them from the ground up. So let's build this one. So we'll start with, we have the first floor columns. They'll go on top of the foundation. We'll leave the foundation out of discussion now. And then we're going to have second floor framing. Okay. The second floor framing really oftentimes is the first floor we're going to frame because the ground floor is slab on grade. All right. Next, we have second floor columns. These are the columns that sit on the second floor. Third floor framing, same as the second. Okay. Fourth floor columns and fourth floor framing. And then finally, the columns that are going to support the roof. I'll roll out here a bit. And then the roof framing. Hey, we got a frame structure now. Not complete, because we want to have some walls so we can keep the outside out and the inside in. So let's show what the walls look like. And there, we got some walls with windows. Remember, when we calculate dead loads for walls at this stage, preliminary stage, we can really neglect the glazing, the windows. We just use the composition of the wall, usually weighs more than the glazing, so we can neglect windows outright. And then finally, we'll have a parapet on top. Okay, we may, depending upon the construction type, have to consider that. So for the purpose of this assignment, you should consider the parapet. And the conservative way to do it is to consider it the same weight as the walls. Okay, so that's a unit weight. So a fair bit of geometry here. And now we have to go through and put this together. But before we do that, that visualization tool helps us out. But before we do that, let's talk about some basics for tributary area. And that's the basic principle here that we're going to use in calculating axial loads on columns. So let's take a look at a real simple example, just a regular table that's 2 meters by 3 meters. And the load applied to this table is 2.4 kPa. Okay? And I have it dimensioned here, an isometric view, and the blue vertical lines are the columns, and then we have 2 meters by 3 meters, and I even put in the dashed lines to show the breakout of the different 1 meter areas. All right. So if I put 2.4 kilonewtons per square meter, 2.4 kPa, that's the same as if I put little boxes on top of my floor that are 1 meter by 1 meter, and each weigh 2.4 kilonewtons. That's what I'm showing there. Okay? And now what I got to do is I got to distribute this load over the 4 legs. Okay. Now I have how many square meters? Well, I got 6. Don't even have to do math. I can just count the boxes. Okay, 1, 2, 3, 4, 5, 6. And so 6 square meters, 6 boxes. Each one supports 2.4 kilonewtons. The total load that table is supporting is 6 times 2.4 is 14.4 kilonewtons. Okay? Notice that the units now go from kilonewtons per square meter to kilonewtons. Since there are 4 legs, and really the geometry is quite simple and uniform, well, it's reasonable to expect that each leg is going to support an equal amount of load. So you take that 14.4 kilonewtons, and we divide it by 4, and we end up with 3.6 kilonewtons per leg. Okay? So a simpler solution is to separate the load from the area and just look at the geometry. Okay, and that's what I talk about geometry. We're really taking apart any loads applied and just looking at the geometry, the measurements themselves. The load is uniform throughout and essentially just becomes a coefficient when we do that. So if I have the geometry, the area, I can multiply by snow load, live load, dead load, and get those corresponding axial loads. That could be very useful. So the principle we use here to determine how much area load each leg or column is going to support is the principle of tributary area. So the tributary area is the area a particular leg or column supports and is bounded by a box defined by half the distance to the next support. Okay. So here's my shaded box, and half the distance from this support to this support is 1/2 of 2 is 1 meter. And half the distance from this support to this support is 1/2 of 3 is 1.5. So I could say that this column supports a tributary area of 1.5 times 1.5 meters squared. Okay, and by symmetry, each column is going to support that load. So if the load applied is 2.4 kPa, the total load on that corner leg is going to be the tributary area it supports multiplied by that 2.4 kilonewtons per meter squared, kPa, kilonewtons per meter squared, the same, 3.6 kilonewtons. Exactly what I previously calculated. Okay, brilliant. Now that's fine for a simple 4-legged table. We can understand, we can visualize it. Let's make it a 6-legged table. Okay, and now we have 2 inner supports. Same principle. You add up the distance, sum of the half the distance to the next support on each side. So for this column, I'm going to support half the distance to this column on this side, which is 1.5, as well as 1/2 the distance from this column to this column, again 1.5, and then 1/2 the distance from here to here, which is going to be 1. And that gives me brackets 1.5 plus 1.5 times 1. Now I'm supporting 3 square meters. So now to calculate the load that this column is supported, I take the area load, multiply it by that tributary area, and I get 7.2 kilonewtons. What about if I had a 9-legged table? And this is very similar to what you're seeing for your assignment. Okay? I'm going to have now corner columns, and I'm also going to have edge columns. All right. So we solved for all the corner columns, no problem. Okay. And we've solved for the edge columns. We know how to do those. Now, there's one other one we have in here. It's an interior column. And this one supports a tributary area of the shaded area, 1/2 the distance on each side to the next support. So 1.5 and 1.5 and 1 and 1. So that shaded area is going to be 1 plus 1 is 2 times 1.5 plus 1.5 is going to be 6 square meters. If the applied load is 2.4 kPa, the total load on the interior column is going to be 6 times 2.4 is 14.4 kilonewtons. Okay. So really, we can look at a building and we could see that, try to identify which column is supporting the greatest load. And invariably, it's most common that it's an interior column with the greatest tributary area. That's going to have to be the largest column selection. But that doesn't mean that whatever I use for that interior column, I can use for an exterior column, because I do have another load on exterior columns I have to consider. Anybody know what that is? The wall dead load. Yeah, there's some wall dead load there, but what else? Because we're thinking gravity loads, downward acting loads. What other loads do we have acting on a building? Wind. Okay. So a lot of times, those exterior columns, actually most of the times, I forget it, all the time, exterior columns have to support wind load and axial loads at the same time. Okay, so we can't just say, well, I sized for the biggest interior column, and that will apply for exterior columns. Well, exterior columns can be much more complex. Any questions on that? Pretty straightforward. This is the basic principle behind calculating the loads for your building. Something else, too, that on this one I can determine pretty quick is that I look at my total area, my floor plan area, and you know in CAD, you can click on your floor plan, right mouse button, and pull up the area for a given floor. No problem. You have that area, you have the load, the weight of the composition, the occupancy load or the weight of the dead load, then you have the total load for that floor. So in this case, I could take this and say I have 6 meters by 4 meters is 24 square meters. And if I do 24 times 2.4, oh geez, I better get my calculator for this. 24 times 2.4, calculator doesn't like me. And that's 57.6. So I'll just write that in here too, just to get us going here. Is going to be 6 times 4 is 24 meters squared, okay? And my load, P, for the interior column is going to be 24 times 2.4, which is going to give me 57.6 kilonewtons. Now, from my calculations that I did, we know that my corner column has a load of 3.6. So I have 3.6 here, 3.6 here, 3.6 here, and 3.6 here. And my edge columns, well, I calculated this one here, which is 3 square meters, and that's 7.2. That's going to be 7.2, and that's going to be 7.2. Now I have these columns, which I didn't calculate, but that's also going to be 1.5 times 2. Well, that's actually still going to be 3 square meters, okay? So really, this one also becomes 7.2 and 7.2, okay? So now if I added up all the column loads, in the interior one we said was 14.4, we could write the sum of all the column loads, 14.4 plus 4 times 3.6 plus 4 times 7.2. Let's see, what does that equal? There, decided to go with sleep. 14.4 plus 4 times 3.6 plus 4 times 7.2, 57.6. Now that's a nice check, okay? So that's telling me when I calculate each individual column load and I can check it against the total area, well, this calculation tells me all the load that's acting at that level. And down here, summing up each of those columns tells me all the load that all the columns support. They have to equal. They have to be the same, okay? So that's a powerful tool to have for checking loads. All right, let's move on. We'll go to the next section here, okay? So now we look at our multi-story building. This is it. And let's start with our example. So in this case, our job is to calculate the snow, live, and dead load components for each column at each level. And we have specified loads. We have a snow load of 1.88, roof dead load of 1 kPa, floor live load of 2.4, a floor dead load of 1.5, an exterior wall load of 0.75 kPa, and we're also going to use that load for the weight of the parapet, okay? Sometimes it could be different, but we're not going to worry about that. And we're going to use a column dead load. We're going to assume our column dead load is 0.5 kilonewtons per meter. And what that means is if you have 0.5 kilonewtons per meter for a 3-meter column, it's going to be 1.5 kilonewtons. Okay. So how do we go about doing this? Well, we have to first look at the geometry for the building. So let's get a quick view of the building here. And I got some elevations, sections. Here's a 3D view with the walls stripped. So we got an idea of that. And this is with the walls. Okay. And so looking at the floor plan, we are laid out grids A to D and 1 to 3. Here's a case where it really is useful to use grid references, because I can reference column A1, column C4, column A3, and I could say this to anybody: you got that plan, you'll know exactly what I'm talking about. Okay? So when we look at this, we need to calculate some tributary areas for that geometry. And I got to slide further down here. Okay. Oh, yes, I should show you this one here. For multi-story design, let's take a look here. This is the principle that's happening for multi-story design. So at the top, I show two horizontal arrows, and that's basically taking the roof area loads and transferring it to the column supporting the roof. And then that load is going to be transferred to the column below, where it also picks up the load from the fourth floor. So that load is larger. And that transfers to the column down below and also picks up load from the third floor. So that load becomes larger. And then that goes down to the column down below, which then sits on the footing. And that's also going to pick up the weight of the second floor. So what you want to remember is that with high-rise or multi-story buildings, that the column loads are additive as you go from top to bottom. And even though many buildings show the same size column from top to bottom, there is considerably less load supporting the upper final level than there would be at the ground level. The reason why we use the same column is just for ease of construction. Okay? And this is what I want to calculate. And I got to do it for each column. And I have, on top of all that, okay, I have 12 columns, and I got to do it supporting 1, 2, 3, 4. So I got 48 loads to calculate. That's a lot of calculations. Now do it for a 100-story building. Do it for each level has 50 columns, okay? It's a lot of calculations. You want to have that organized. You want to have it presentable, or have it so that you can very quickly look back and find it, okay? So this is screaming. You want to use a tool, Excel, okay? But before we can use Excel, we have to understand the calculations on how to figure this out. We have to be able to visualize it, put numbers to that visualization, to the geometry, and calculate that. And that's what we're going to do first. We can take advantage of some repetition. There is symmetry in the building. And I can see that here because we look across. A to B is 4.5, B to C is 5.5, and then C to D is 4.5. And then down this side, I have 6 and 7. Well, by symmetry, column B1 and C1 are identical. Okay, so I only have to calculate for one of them. And column A1 and D1 are also identical. I'm going to call those C1. Notice how I'm labeling them at a 45-degree angle. Similarly, A2 and D2 are going to be same. They're going to be C3. And A3 and D3 is going to be C5s. And then these two here are going to be C6s. And then in the middle, the interior are C4s. So essentially, I've taken 12 columns, and by symmetry, I only have to calculate for 6. That just cut my work in half, right? So, getting started. I use this here, stand by. I want to use a table that's going to help me, okay? And I'm going to use this table here. And this table shows me some information from left to right across the top. I'm going to calculate, and then down the columns here, I'm going to put in for each row the different columns, C1 to C6. And then the next column is going to be for each column, what is the tributary area? And then I'm going to look at wall or parapet tributary width. So how much is that column going to support of the wall or the parapet? We've already identified that exterior columns are going to support wall. I got to consider that. That's also going to be a function of the wall or parapet height. Need to know the column height because I'm going to have a dead load for the column. I need to know the dead load for the wall in kilonewtons. And I also have to calculate the axial load for snow and the axial load for live. And then with these different dead loads, I'll be able to add them together and get a total dead load at that level. So this is what I'm going to want to fill in. And it all starts with that tributary area. Let's get cooking with that tributary area. Here. All right. So for column C1, and I got to be careful here so I can show it. I'm going to flip this around. I'm not going to type anything. All right. So for column C1, I'm going to use blue. And I've already drawn in some dashed lines here, which represent half the distance to the next support. Okay. So I look at it that for C1, it's going to support this area here. Let's just, before we get going here, that part and that part. And this distance here, I'll just write that in here. That's 1/2 of 4.5. And that's going to be equal to 2.75. Sorry, correction, 2.25. Okay. And then I'm going to have half the distance here, which is 1/2 times 6. That's the 6 there. And that's going to be equal to 3 meters. Okay. Now, do I have everything included there? No, I don't. Because just having that corner for the tributary area is not enough. Drawings indicate that we have an extension around the perimeter beyond the grid line equal to 2.2 meters. I'm not going to use arrows, that would be just confusing. So with my tributary area, not much complexity there. All I need to do is add in that value. So here it's going to be 0.2, and here is going to be 0.2. So the tributary area for column C1 is going to be defined. Can I put this up in here? Sure, I can. 2.25 plus 0.2 is going to be 2.45, and here is going to be 3 plus 0.2, which is 3.2. Okay, and I'm going to write it down here. First off, I'm going to shade this. A little bit smaller. Okay, and so now below here, scroll down a little bit. I'm going to be calculating tributary area per column. And I'm going to write down here C1, C2, C3, C4, C5, and C6. That's my column and my tributary area. And for C1, we said we're going to write in, it's going to be 1/2 times 6 plus 0.2. That's the overhang. Multiply by 1/2 times 4.5 plus 0.2. And that's going to equal, and I got enough room down here, that's 3.2 meters times 2.45 meters. And that's going to give me 7.84 meters squared. Okay. And something else I can do here is number of columns. And for number of C1s, how many C1s do I have? I got 2. And I can even put in here total tributary area. Whoops, that didn't work well. And all this is 2 times 7.84. That's going to give me 15.68. A method to my madness for doing that. So that's C1. Okay. And I can go so far, go to my next page here. Well, I have my tributary area here, and I'll just even rewrite it. 1/2 times 6 plus 0.2. And that's going to be multiplied by 1/2 times 4.5 plus 0.2. And that equals 7.84. All right. Now let's do for the next one. That's C1. What about C2? Well, I'm going to use green here. Now C2, let's sketch in the tributary area that it supports. So it's going to support 1/2 this dimension here. And that gives me 2.75 meters. Okay. And this dimension here, which is 1/2 times 4.5, which is 2.25. And this dimension up here. Well, guess what? C2 has the same dimension here for tributary area as this dimension here. So I'm going to shade in that area. Can I get somebody to close the door, please? Thank you. So now for C2, if I add this together here, this dimension is going to be 5 meters. Okay. So I'm going to be 5 meters times 3.2 for that tributary area. Notice I still have the extension here, but I don't have it in this direction. Let's write that down here. So for C2, I'm going to put in some brackets here. Let's make that blue. And I'm going to write it like this. So this is C2 is going to be 1/2 times 4.5 plus 1/2 times 5.5. Close brackets. So that's one direction. And I'm going to multiply that by 1/2 times 6 plus 0.2. And that's going to equal 16 meters squared. How many C2s do I have? Well, there's 2 of them. So 2 C2s here and here. So that's going to be 32 meters squared. Okay. So now we've been able to solve for column C1 and C2 for tributary area. Now we want to move on to the next one, which is C3. Note that once we have this one, we don't have to worry anything on this side. So for C3, I'm going to use red. And C3 is very similar to C2. It's an edge column. Okay. And my dimension here, this dimension here, is going to be 1/2 times 6 plus 1/2 times 7. I'm going to make sure that doesn't show up. That sure looks like a 1 there. 1/2 times 7. So that's going to equal 6.5 meters. And then this dimension here, well, I already have the other dimension, 2.45. Okay. And I'll just put that in here to show it. And I'll state it. And that's the tributary area that C3 supports. You start to see that as we put this together, the tributary area for each column, as we've developed this, has to cover the whole floor plan. There can't be any overlap, and we can't miss any areas. So for C3, I'm going to write it in here. Calculation down here. And it is 1/2 times 6 plus 1/2 times 7. Close bracket, multiply by 1/2 times 4.5 plus 0.2 for that overhang, and I get a value of 15. I'm going to take it to the final decimal place, 15.925 meters squared. And that is going to come, I got how many columns of those? 2, and I think that comes out to 31.85 meters squared. All right. So I got 3 columns done. I got 3 more to do. So we're going to move on. C4, where is our C4? C4 is probably the simplest because it's an interior column. Now, since I have in this area some writing, I'm just going to do it in here. I'm going to switch back to blue. I'm out of colors. So this is the amount of area that C4 supports. And if I write in this dimension here, that dimension is going to be 1/2 times 5.5 plus 1/2 times 4.5. And that works out to be what we had. Well, it's pretty much the same as this one. That's going to be 5.0 meters. I'm not making any assumptions because I know I'm doing an interior column, so it may be different. All right. And the other dimension is this one here. Well, we already calculated that, so that's the same as here. I'm just going to put that in as 6.5. Okay. So for column C4, I can write it 1/2 times 5.5. Whoops, messed that up. Plus 1/2 times 4. Times 1/2 times 6 plus 1/2 times 7. And when I calculate that, I get 32.5 meters squared. How many columns of that do I have? 2. So the total area by C4s is 65.0. Okay. So the next one I got to do is C5, another corner column. All right. And so this one I'm going to use, what color should I use now? We'll go back to green. So this is the tributary area for C5. And this dimension I already have. I don't have to redo this one. I'll put it down in my calculation there, but it's 2.25 meters. Correction, 2.45 meters. And then this dimension here, 1/2 times 7 plus 0.2. And I got to be careful because I'm going to need room for my C6. 1/2 times 7. So that's going to be 3.7 meters. Okay. So now I plug those numbers in for C5. And I'm going to have 1/2 times 7 plus 1/2, oh, sorry, plus 0.2. That's all I need there. And I'm going to multiply that by 1/2 times 4.5 plus 0.2, the corner column. And that gives me 9.065 meters squared. How many C5s do I have? Again, I have 2, 18.13 meters squared. Okay. C6 is the last one. C6, and we use red for that. It's not going to give me a conflict. right? And that dimension along here, well, I hope I don't have to show that outright. That's going to be still 5 meters here. Already have that. And this one here, going to be 3.7. And but just for fun, I'm going to spell it out in here for C6. 1/2 times 5.5 plus 1/2 times 4.5, close bracket, multiply 1/2 times 7 plus 0.2, and that gives me 18.5 meters squared. I have 2 of those columns, so that's 37 meters. Take that to the hundredths place. Now, I've completed all my tributary area calculations. All right. The ones that are left out, we've already done. They've been duplicated. And now I want to check. I'm nervous about my math. I'm an engineer. I like to sleep at night, make sure I got things correct. And simply put, when you're designing columns, if you got your geometry wrong, you got your tributary area wrong, your design is going to be wrong. You're either going to be over-designed or under-designed, but you will not be correctly designed. So we need to verify that. So one way I can do that, because looking at this doesn't mean anything. But one thing I can do is add up these numbers. So 15.68 plus 32 plus 31.85 plus 65 plus 18.13 plus 37 gives me 199.66 meters squared. So I want to check my area calculation. Overall floor area. And my dimensions for the building, I'm going to have to define that. So we should have this information already. I shouldn't even have to calculate it, but beware, sometimes dimensions are only to the grid line, so we need to make sure we include all the overhangs. So I'm going to have 0.2 plus 4.5 plus 5.0 plus 4.5 plus 0.2. And that's going to give me, I believe, 13.4 meters. Okay. And then the other dimension, and it's going to be a little trickier to nail down. Well, I should be able to do it. You should be able to get this dead on. And this dimension is going to be 0.2 plus 6.0 plus 7.0 plus 0.2. Okay, that's going to be 13.4. Oh, I think I might have got a mistake here. Thank you. Sorry. Oh, right. You know, geez, there's my mistake right there. I had 5.0. That is 5.5. So 4.5 and 4.5 is 9, and 5.5 is 14.5, 14.9. Very good. Thank you. So now my tributary area, overall tributary area is building 14.9. Let's change that to blue. $14.9 meters times 13.4 meters, and I come up with 199.66 meters squared. Does that work? Exactly. Same, check, okay. That's an important check because that tells me that for each column I have the correct tributary area. I guarantee I haven't made a mistake, but it tends to align. Okay? That's the kind of stuff that you want to be doing, especially with math. All right, so going back to my table now, that step done, I'm ready to start filling in these numbers. So tributary area for column 1 was 7.84. This one was 16. This one was 15.93. And what was that? 15.925. Let's see here. Yeah, 15.925. I'm rounding up. At this point, it really doesn't make too much of a hill of beans difference, but for 15.925, this one is 32.5, and this one was 9.065, and this one was 18.5. Okay, so that's going to help me with that. Now, the next one I got is I got to fill in some of these other items. Okay, and the next one is the wall or parapet. And this is wall or parapet height. Okay, well, it's a wall for floors, and it's a parapet for the roof. And what I want to do is I want to identify which level am I doing this for? Well, I build buildings from the ground up. I design them from the roof down. So this is the roof level. Okay. So now when I look at my building, what's the wall or parapet tribute? Well, let's start with the height because that's going to be the easiest. Now I need to go to this diagram here. Actually, we got to go to this one here. And we see here, this is the wall correction parapet height. And this is the load that is being applied from the parapet onto my floor. So that is what I put in there for that 1 meter in that table. Okay, so for the roof level, it is going to be, I'm going to cross out wall. And it's the parapet, and the height here is going to be 1.0 meter. All right. The next thing I want to look at is, can I apply that to which columns? This is a bit of a tricky thing. So where does that parapet go? And I'm going to go back up to my first diagram way at the top, my first floor plan, just so I can use it. And this is going to be part of the next step, which is determining the length of wall a column supports. Well, the first thing we can recognize is that only exterior columns, and that includes edge and corner columns, support wall or parapet. And for this building, it's going to be around the perimeter. Okay. So interior columns, this is what I want to make a note of, is interior columns, which is C4 in this case, do not support wall. That makes sense. They're interior. So I'm going to go back to my table down here. And for my interior columns, I'm going to say here that I got for C4 is going to be 0 and 0. We're not supporting any height or any part of that. The rest of them will support 1 meter in height of the parapet, because the parapet height is uniform all around the perimeter. So the next step now is how much width of that wall is it supporting, or parapet? That's where we come up here, and we're going to have to look at 5 columns. Finish up here in a second. Take a break. And when we look at, for column C1, from our previous calculations, we know this dimension is 2.45. And this dimension here is 3.2. Okay. Now, the amount of tributary wall that it's supported, I'm going to just sketch it in like a line. So this is the wall, the parapet wall, the amount of parapet wall that it's supporting. Okay. What does that look like? Now let's go back down to here. Help us visualize this. Okay. Now look at the wall here, and this is the corner column. And half the distance to the next column, which is over, where would that be? Oh, I got it. Half the distance this way, and half the distance that way. And do I got that correct? Let's just see here. That's going to be going that way for columns. And I think I just got 2 windows in there. 2, 3, 4. Got too many columns. Put it right in there. That ain't quite right. And so we take half the distance. That's going to come down here, and half the distance here. And this shaded area is the amount of parapet that is supported. It's a parapet. Right. So to calculate that weight from the parapet, going back here, I got to take the amount of length that it's supported and multiply it by its parapet height. And that length here is going to be 2.45 plus 3.2. Well, 2.45. Do not multiply it because it's not area, it's just length. And that's going to give me 5.65. Okay. So that's what I want to enter in my table. So the amount of wall supported. Going to be 5.65. Let's look at C2. I think I actually can do it here. For C2, the amount of wall supported is going to be that 5 meters. Do that with blue. keep consistent on my lines here. That's 5 meters. All right. And I'm going to save the step I'm going to do also for C3. That's right to here. That dimension there, we know from the tributary area calculations, 1/2 times 6, 1/2 times 7. So that's going to be 6.5 meters. Okay. So I'll transfer those over. Oh yeah, I can do something else here too. Is that for C6, if you notice, C6 is going to have the same amount of wall support as C2. And that's going to be 5 meters. All right. So maybe 5, 6.5, and 5. Let's transfer those, and we can go on break. C6 is also 5.0. C4 has 0. And now we got to look at C5, the corner column again. And that one, I'm going to try to use a different color. What other colors do I have here? There, that's a good one. So for C5, well, we know that dimension again. From tributary, we already calculated that's 1/2 times 7 plus 0.2 for the overhang, which is 3.7. And this dimension here, once again, 1/2 times 4.5 plus 0.2, which gives me 2.45. Okay. So the amount of wall that's supported here is going to be, let's write that here, C3 supports 3.7 plus 2.45, which is equal to 6.15 meters of parapet or wall. Correct, C5. Correction, thank you. Thank you, C5. Hard to talk and write at the same time. So I'll put that one in here, 6.15. All right. So that takes care of the wall parapet height. Okay. Column height. Well, I got to go to my sections for that. And this building is, they were quite generous because it's 3.2 floor to floor. So I'm going to include that in my calculation here. And every column's the same height. So that's good. Well, I do believe that that is all the geometry I require. Something interesting as well, that once I have that, okay, so I can look at an elevation, stop for a break. I'll look at the elevation. This is basically what I'm supporting. Note that the wall we consider is 100% to the floor below. The walls are stood up. And when we do this calculation, we don't typically assume that the wall would be hung off of the roof. Walls bear 100% on floor deck below. They are not hung. So what does that mean? Well, that means, and because of the symmetry in the building and from floor to floor, this makes my life easier. So that's a heck of a lot of work to do all this. Well, now I go for my next level down below, which is going to be my 4th level. And for here, same columns because the columns all line up. That's what we want. Tributary area, because of symmetry, is the same. 7.84, 16.0, 15.925, 32.5, 9.07, and 18.5. And then my wall tributary width, the amount of perimeter that that column supports, that's the same too. 5.65, 5.00, 6.5, 0 for the interior column, 6.15, and 5.0. Then my wall height, in this case, I'm going to write this in red to make it jump out because the parapet height is supported on the roof deck. That's 1 meter. But for the wall supported on the 4th floor is 3.2. Okay. And then my column height is also 3.2. And this table here, you know, if you're smart, don't fill in that level, fill this in and photocopy it 2 more times, and then fill in 3 and 2. Okay, because they're identical. Right? So the next step, what we're going to do after the break, is we're going to calculate the axial loads due to the wall parapet. And that's going to be the parapet height times the parapet length that's supported, and we'll multiply that by the wall unit weight. And then the load for the column, we're going to take the unit weight of the column per meter, multiply it by the column height. The deck, we'll take the tributary area, multiply it by the area dead load, and the snow load or the live load correspondingly. Keep in mind, you'll never have both of these on the same level. It'll either be snow, which is always on the roof, and live on the floor, because it doesn't snow inside. Fundamental principle we can count on. So let's take a break there. And I'm going to stop the meeting. I think. Stop the recording. We'll pick it up after the